In this problem, we have a long solenoid with a radius of 1 centimeter. So here's our little solenoid right here. We know the turns per centimeter, which you need to convert to per meter. We know the current is varying over time at this constant rate. We're going to find the magnetic electric field out here, all right, out here in an area around the solenoid at a given distance. So this is a concentric circle around the solenoid, and we're trying to figure out what the magnetic field is electric field is out here. Well, we know the magnetic field in a solenoid from chapter 12 is confined to just the interior of the solenoid, and there's none out here. All right. So let's take a look at where we are. All right. If you watched the last problem, you know, B field for a solenoid is permeability of free space times the turns per meter for the solenoid times the current. And if we then look at what is the magnetic flux in the solenoid, well, the magnetic flux in the solenoid is just going to be that B times the area of the solenoid, so mu naught in I A, or I'm going to put AI, right? And we know that the electric field right, from, remember our review of the chapter, electric field is minus d phi dt. Minus d phi dt. And so, I mean, we can get to that really quick, right? Minus mu naught in a di dt. And I say di dt because the area of the solenoid is not changing. The current is changing, and we know the rate at which the current is changing, which is di dt, which is 1.76 amps per second. And so we've got the magnitude of, we've got this integral of E dot dl, right? Now, if you remember from the work we did with Gauss's law and Ampere's law and other things out on the other chapters, in the integral of E dot dl out here around the solenoid is going to be, the electric field is going to be constant out there, right? There is no radial component. It's all going around the solenoid, all due to the symmetry of the problem. We can rewrite this integral as simply E times 2 pi r, where r is how far away from the middle of the solenoid we are, all right? And so in a di dt, all right? And so we want the magnetic electric field out here, away from the center of the solenoid. All we have to do, E is solve for E in A over 2 pi. I took out the negative because we're after the magnitude. Make that look a little prettier. And there you go. And that's how you get there. I hope this works for you.